Log on, tune in, find out. Another good idea from Cambridge.
University of London, but also, and I think this has a bearing on what I'm going to be talking about, and I forgot to put the mic on, so I'll start again. Okay, I'll start again. I'm Sandra Eldridge. I'm Professor of Biostatistics at Queen Mary University of London, but I'm also, and I think this has some bearing on what I'm going to talk about, the Director of a Pragmatic Clinical Trials Unit, which means I spend an awful lot of my time with clinicians trying to sort out practical and logistic problems in trials, and that's really where this talk comes from. So I want to thank Alan and Mike, because they've already said some of the things that are on some of my slides, and it means I'll be able to whip through those quickly and I won't talk for too long, which I do have a tendency to do. So just to give you a bit of an outline, I was going to talk a little bit about an introduction to sample size calculations, but since you've heard that twice already, I'll probably skip very quickly over that. But then a bit of background to trials in health services research, and particularly in primary healthcare where I work, to give you a bit of background of the sort of scope of some of these trials. Then I'm going to be talking about accounting for variation in cluster size, and then a little bit about intra-cluster correlation coefficients. So I'm going to skip over this because Alan's already and Mike have given you this adjustment factor for adjusting for sample size for cluster randomised trials. And this is what people normally do when they're doing a cluster randomised trial, adjust using this design effect, which has the intra-cluster correlation coefficient and the cluster size in it. And usually it's been assumed that the cluster sizes are all the same, and Alan gave you this expression for the intra-cluster correlation. I wanted to start off just by having a look at actually how many trials take account of clustering at all. So how many trials use that formula at all. And here on the left-hand side of this slide, you can see a lot of reviews of these trials which were done over some considerable period of time, but the trials included in these reviews were all published between 1973 and 2002. Now the grey bars show those trials that account for clustering in the analysis, and you can see certainly on this left-hand side they're much higher than the bars for the trials that take account of sample size calculations, take account of clustering in the sample size calculations. So trials published between these dates, actually about a quarter or so, take account of clustering in the sample size calculation. If we look over this side, you've got trials published between 1998 and 2009 included in these 6 reviews, and you can see that there's been some improvement, but it's still not great. I think the average is at about 50% or so of trials taking account of clustering in the sample size calculation. So when I say that's the usual way people do it, actually a lot of people don't even do that. Sorry? Is that the effect of Alan's book? What, the change? Yeah, one likes to think so. Okay, but I think for those of us who do take account of clustering in the sample size, there are very practical issues for investigators, and one is, what do we do about sample size calculations if the cluster sizes are likely to vary? And one of the things you can do is use mean cluster size in place of that fixed cluster size in the design effect, but that will tend to underestimate the sample size required. And the second big issue, I think, is how on earth do we estimate the intra-cluster correlation coefficient, and we've already had a short discussion about that previously. So just to give you a little bit of background to the sort of trials that I work on, and these are very similar to the trials that Mike's mentioned, because actually in health services research, and particularly in primary healthcare, these trials are very, very popular. So a lot of the trials that come through our pragmatic clinical trials unit are cluster randomised, and that's because they're asking these sorts of questions about what happens when we give education to health professionals, when we change the organisation of primary care organisation, or with what happens if we add new staff, and it's just not possible to do anything else very often. So to give you an example, this is the Electra trial. If you look carefully, you'll see that there's a little bit of license with this acronym. And this was a trial looking at asthma specialist nurses. So asthma specialist nurses were introduced into the intervention practices. This was again a trial where we're randomising UK general practices. And the idea was that these asthma specialist nurses would then have the responsibility for treating individuals with asthma, but they would also offer education and support to the general practitioners in those practices. And this trial was published in the BMJ in 2004. Just give you a bit of background to the way that recruitment was done in this trial. First of all, we recruited 44 practices, and when the practices were recruited, we then recruited individuals in two ways. One is we took those individuals who had either pitched up at accident and emergency departments with an exacerbation of asthma in the previous 2 years, or individuals who attended accident and emergency or their general practice with an exacerbation of asthma in the 1 year following the start of the trial. Now, you might say that those people that we were recruiting post the recruitment and randomisation of the practices, possibly there might be some sort of bias in the identification and recruitment of those individuals, as we've heard. We didn't find that much in this trial, and I think maybe you can disagree with me, but I think possibly because we were recruiting them via their attendance, they had to attend at A&E or the general practice with an exacerbation of asthma. So it wasn't like identifying more individuals with diabetes. There was a stricter, if you like, inclusion criteria there. The range of cluster sizes in this trial was between 2 and 28. So that's quite a large range, with a mean cluster size of 7.78, and as you'll see a bit later, a very useful measure of the variation in cluster size is the coefficient of variation of cluster size, and in this case that's a standard deviation over the mean was 0.64. So we have got a reasonable variation in the numbers recruited in each cluster. One of the other things that happened in Electra was when we did the sample size calculation, we assumed our ICC would be 0.05. The actual ICC, observed ICC in the trial, was minus 0.0056. I think in this particular trial, although Mike has said there are some trials where you can get negative ICCs, I think in this particular trial we assumed that negative is due to sampling error. Nevertheless, the ICC is much smaller than we had anticipated. In the analysis, we actually set the negative ICC to 0, i.e. we assumed there's really no clustering. So what I'm going to do now is just set that one trial in the context of other trials in this area, and I'm going to use 5 pieces of work to do that. 3 reviews that have been undertaken in our department, one published in 2004, then another review in oral health, and that's in press at the moment. That's something done together with Alan Donner, and the researcher on that was Rob Froud, who's in our centre, and then a review that's in progress at the moment, and Carla Diaz-Ordaz, who's in the middle of the audience, is leading on that one. And at the moment I've got a PhD student who is reviewing sample size methods for these trials, looking at the methodological literature. So I'm going to show you some very, very early work. She's only just started. She's doing it part-time, and she's only been with us since January. So this is very early stuff that's coming out of her work. and then a methodological paper that we published in 2006. So taking the first review of trials in primary care, and these were trials published between 1997 and 2000, and just to give you an idea of the number of clusters in these sorts of trials, this is a very skewed distribution, but the median of this distribution is 34, and mostly you've got trials there where the number of clusters is below 100, and usually well below 100. Electra had 44 clusters. If we look at the size of the clusters, and again this is quite skewed with a average size of the clusters, a median of 32, and Electra was a bit smaller than this with a mean cluster size of 7.78. In terms of whether the cluster sizes were equal or unequal, less than a quarter of trials actually attempted to have equal cluster sizes. All the other trials recruited people as they could from the different clusters, and the usual method of recruiting is to recruit either from registers, and that was one of the methods I showed you in the Electra trial, or using incident cases, people who pitch up at the surgery or at A&E. And in that case, you might assume that it's reasonable to think that the cluster size that you get in these trials might be approximately proportional to the total size of the cluster. So if you've got a large general practice, then and you're recruiting from it, you might get more patients from that general practice than if you're recruiting from a small general practice. Seems fairly obvious. This is the data from the methodological paper that we published in 2006, and this shows you the distribution of cluster sizes in 6 different trials. And I wasn't sure how well you'd be able to see the actual figures on the diagrams, so I've put up here the coefficients of variation of these of cluster sizes for these 6 trials. They vary between 0.42 and 0.75, and actually if you look at the coefficient of variation of cluster size of UK general practices, and these trials are all based in UK general practices, if you look at the overall coefficient of variation, that's in fact 0.65. So some of these trials the variation was slightly less than you might expect, and sometimes it was slightly more. But 0.65 would seem a reasonable guess at the coefficient of variation of cluster size for trials randomising general practices. When we look at ICCs, these are 150 ICCs, and they're taken from various sources, but again these are randomising general practices or family practices, and you can see that the ICCs vary, some are negative, most of them vary between 0 and 0.3. There's one outlier here at 0.57, and there's a few that are negative, and our Electra trial came in this bunch where the observed ICCs are negative. I mean, most people working in this area would say that the reason for the ICCs down this end is sampling error, and I would also say that I think the reason for the ICC up this end is sampling error. I believe the ones in the middle. But not many trials actually report ICCs in analyses, and this is looking at the 3 reviews. In the review of trials in primary care, only 7% of those trials actually reported an observed ICC. So actually very difficult to get a handle on what ICCs people are actually finding in their studies. The oral health review focused on much more recent trials, and there it's better, about a third report ICCs, but still that's not as many as perhaps we would like. And there is an extended consort statement for cluster randomised trials, which actually published in 2004, and that recommends that people should report the ICCs in their trials, but still there are an awful lot of trials where people are not doing that. And one of the reasons why people like to see these ICCs reported is for the very thing that I'm talking about. They give us a better handle for future trials and what our ICCs might be. So just to give you a sort of idea about the difference between the ICCs that people use in sample size calculations and the observed ICCs, this is quite an interesting exercise for me. These top 4 trials are all trials that I've been involved in, and so I thought, well, I'll go and have a look at what we assumed in the sample size and then what we found in the trial itself. And you can see for those top 4, and honestly, I just picked them out, not randomly, but I picked out 4, not deliberately. But you can see for those top 4 that the ICC we used in the sample size was in all cases considerably larger than the ICC, observed ICC. I've got no explanation for that, but that is in fact what happened. So all of those trials, there are other factors that obviously go into the sample size calculation, but all of those trials on the basis of the ICC, we would have got overpowered trials because we would have had a sample size that was larger than we actually needed. The one at the bottom I actually did go looking for specifically, and this is a trial where they estimated their ICC to be 0.02. Actually, when they did the analysis, when they got the results, they found the ICC was much, much higher. To give some idea of the sort of effects that this has on the size of the trials, for the Electra trial at the top, we increased our sample size by just under 30% in order to allow for clustering. So without clustering, we might have gone for 34 clusters. We increased it to 44 because we thought that this would be our ICC. If the ICC was actually 0, then we would have recruited 10 more clusters than we needed to. For the trial at the bottom, they were doing the smoking cessation in schools where the clusters were much, much larger. And so if you look at those 2 ICCs, actually they probably would have needed a sample size about 4 times as big as they actually had to detect the difference that they wanted to detect. Okay, so in summary, Electra's not untypical in terms of the number of clusters and the cluster size or the unequal cluster sizes, and it's also not untypical in that the observed ICC was not very close to the ICC used in the sample size calculation. So what to do about some of these things? Well, the first thing is, what methods can we use to adjust the sample size to account for variable cluster size? The second thing is, how can we get some information about the variability in the cluster size? And the third thing is, how can we get some information about the ICC? And this is the review that my PhD student Claire Rutherford is currently undertaking as part of her PhD, and this, as I say, is at a very early stage, so don't remember these numbers, because when you see it published, the numbers may be slightly different. But at the moment, she's found 58 papers focusing on the sample size in cluster randomised trials, and of those 58, only 14 are papers which allow for variation in cluster size. All the rest assume that the cluster sizes are fixed. And of those 14 papers, and again this is quite approximate at this stage, 5 papers rely on knowing the actual sizes of the clusters in advance at the stage when you do the sample size calculation. In most cases, I would think that that's not very realistic. 4 papers are actually based on knowing about the coefficient of variation of cluster size in advance, or being able to estimate that, but they assume that the analysis weights by cluster size, so every individual in the study is weighted equally. And there was a question earlier on about the efficiency of different analyses, I think. And so there are 5 further papers which I've just sort of vaguely called other methods, and what they do is use their sample size is based on a method of analysis which is more efficient than assuming that the analysis weights by cluster size. Okay, what I'm going to show you is the method using the coefficient of variation, assuming the analysis weights by cluster size. That's not as efficient as some other methods of analysis. So what this method of sample size calculation actually does is it overestimates the sample size that you would need. And it does that by a very simple adjustment, which is the advantage. We just have to add this into the inflation factor. This is 1 plus the coefficient of variation of sample size, of cluster size. And it's been shown to be appropriate for continuous and binary outcomes. So it's a very simple adjustment. The problem is that you have to know this extra piece of information for it. You have to know the coefficient of variation of cluster size. Because of the way that this formula operates, there's really no need to use the adjustment if your coefficient of variation of cluster size is less than 0.23, and the reason is because if your coefficient of variation is less than that, you have to adjust your sample size by less than 5%. And given what Mike's already said about sample size calculations being a bit of an art rather than a science, there's probably no need to adjust in that case. The other methods, as I've said, use more efficient analysis, but they also result in an approximation to the sample size needed based on the coefficient of variation of cluster size. And because they're assuming a more efficient analysis, they result in a smaller sample size required. So they're strictly more appropriate if you're using that kind of analysis. And most cluster randomized trials do use individual level analyses using generalized estimating equations, which Mike showed you, or using mixed effects models, and that type of analysis is almost universal now in in cluster randomized trials, whereas the analysis weighting by cluster size is very rarely used. So, I mean, this is just one graph. I could have showed you a lot more, looking at what difference it makes whether you use this, whether you use a formula which includes this extra term, or whether you use a formula which is slightly more complicated but is also based on the coefficient of variation of cluster size. And so the red line at the top gives you the design effect if you're weighting by cluster size. So if you look up the side here, you can see the design effects, and this is for a mean cluster size of 10 and a coefficient of variation of 0.65, because that's frequently the coefficient of variation that we find in these trials. So weighting by cluster size, that's the red line. If you use the approximate formula, which is based on using a more efficient analysis, your design effect is along the green line, and ignoring the variation in cluster size, you get this design effect here. What you can see is that these figures down here are ICCs. So what you can see is down here at the bottom, where the ICC is quite small, and it often is for these trials, then the two methods give you very, very similar design effects, but that's because your mean cluster size is quite small. When your mean cluster size is larger, then these two things diverge, but they also diverge as your ICC becomes larger as well. So the discrepancy between those two depends on a number of things, but if you've got relatively small cluster sizes, then the two methods don't give very different results. Okay, so then I thought I'd have a look and see actually what people did. Now there are hundreds of cluster randomized trials, so it's very difficult to go and look and see actually what people are doing by looking across all the trials. But I looked at the papers, those 14 methods papers that take account of variation in cluster size in some way. And this middle column shows you the middle column shows you the total number of citations of these papers from Web of Science. And so the methods that use that are based on knowing actual cluster sizes in advance, those have a total of 72 citations, and of those 12, this is just very quickly going into Web of Science and looking at the titles, I think 12 of those are citations by trial investigators. It's not to say that they actually used this method in their trial, but they looked like people who were about to do trials. For the methods for the papers which use coefficient of variation and assume that you're doing an analysis weighting by cluster size, there's 75 citations, and 16 of those are cited by people who might conceivably be going on to do trials. The other methods where people are assuming that you're doing a more efficient analysis, there are 25 citations, and only one of those is somebody who might be going on to look at a trial. To be fair, I mean these are much more recent papers, so we wouldn't expect them to have so many citations. But even this one citation, this is not related. I did have a look at that one, and it's not related to a cluster randomised trial. So my assumption is that if people are using these methods, they might cite the papers that originally set them out. I mean, that might be an incorrect assumption, but I think it indicates that there are not very many people as yet who are taking any of these methods on board. Okay. Even if you are taking these methods on board, one of the issues, I think, is this issue about how on earth do we get information about variability in cluster size. And one of the ways that you could do that is to get information from previous studies. And I think, for example, in primary care, there's now quite a lot of information about the coefficient of variation of cluster size, as I showed you, but in other areas there's very little. You can do a modelling exercise, and in the methodological paper in 2006 we actually did this, trying to work out what you think the distribution might be based on the distribution of whole cluster sizes in the population, based on your sampling, recruitment, dropout and non-response that you think you might have within the trial. That's the sampling, recruitment, dropout and non-response both of clusters and of individuals. When we did this in that paper, we got very, very similar results to just assuming that your coefficient of variation of cluster size is going to be what the coefficient of variation of cluster size is for the whole clusters. One of the other ways in which you can estimate the variability in cluster size is simply to try and estimate your minimum and maximum cluster sizes, work out the standard deviation from that, and then get your coefficient of variation from that. And actually that's the method in most of the trials that I'm dealing with now. That's the method that I use. I ask people what they think their minimum and maximum cluster sizes are going to be, and work out a standard deviation from that, and work out a coefficient of variation of cluster size from that, unless they're doing a trial in primary care, in UK primary care, randomising general practices, and then I will tell them what I think the coefficient of variation will be. Okay, so in summary, most cluster randomised trials have variable cluster sizes. There are methods that exist to account for that, and they probably should be used. The most commonly used method is the method which assumes that you're doing an analysis weighting by cluster size, and it's conservative. The methods rely on an estimate of the coefficient of variation of cluster size, and this can be approximated most easily using minimum and maximum cluster size values. But the other issue that I mentioned that needs to be addressed is the estimate of the ICC. And we've already touched on this in the other talks. How do you estimate what you think your ICC will be? Well, one way is to guess. But one of the methods which has become increasingly popular over the past 20 years is to look for a single estimate of your ICC from a previous study or from a pilot study. It's quite a popular method, but there are some drawbacks in trying to estimate your ICC from a previous study, depending on the size of that previous study. There are a number of ways I could have showed this. Previously I showed it empirically. This time I decided to show this information. This is using an analytical approximation to the confidence interval for an intracluster correlation coefficient. And what the graph shows you is up here, the width of the confidence interval. Remember, we're looking at ICCs round about 0.05, 0.03, 0.01, and in some trials it can make a lot of difference whether your ICC is 0.01 or 0.05. So what these show you is the number of individuals in a study, and along here you've got the number of clusters in the study. So what you can see, if you've only got 25 individuals in your study, and it doesn't make sense to have, obviously, to have a large number of clusters if you've only got a small number of individuals. But if you've only got a small number of individuals, then the width of the confidence interval for your ICC is absolutely enormous. You just cannot estimate any sort of accurate ICC on that basis. As the number of individuals in your trial goes up, so the width of your confidence interval gradually decreases, but even when you get down here to 200 individuals in your study, the width of the confidence interval is still about 0.2, and that means that you're really not terribly certain what value your ICC is going to take, and so there's a lot of uncertainty around what you put into your sample size calculation. So what are other methods of obtaining ICCs? One of the things that you can do is again look at what people have previously found in terms of ICCs, but not look at single ICCs, but look at patterns in ICCs. And this has been done in a number of papers. And those papers have generally had consistent results in three respects. One is they found higher ICCs for what are called process measures rather than clinical outcomes. And so a process measure would be something like, does an individual have their blood pressure measured? And the ICC for that would generally be higher than the ICC for actual blood pressure. People have also found that ICCs are lower for clusters that are naturally larger. So ICCs are generally lower for communities than they are for general practices, and they're lower for general practices than they are for much smaller clusters, households and families. And the third result, which has been shown in a couple of papers, is that for binary outcomes, there are higher ICCs if the prevalence is nearer to 50%, and lower ICCs if the prevalence is nearer to the extremes. This is an interesting quote from a paper written by Adams and others in 2004. The precise value of an ICC for a given outcome can rarely be estimated in advance. That doesn't sound like very good news. Studies should be designed with reference to the overall distribution of ICCs and with attention to features that increase efficiency. The other thing that you could do is to take, if you have several ICC estimates, previous ICC estimates, you could combine them in some way. And there is a very nice paper by Rebecca Turner and Simon Thompson, and I can't remember if there are other authors on it as well, in 2005, which looks at taking several ICC values and modelling those and producing a distribution which could then be used as a prior distribution. Okay, so I'm going to skip over this, I think, quickly. This is an example. I won't go through what the study is about, but I'll just show you the results very quickly. So this is information like the information I showed you earlier for Electra. This is information from another trial where we were trying to support general practitioners to increase the number of women coming to their surgery identified as victims of domestic violence. A lot of women consult general practices with headaches, depression, injuries, all sorts of things. Actually, the issue is domestic violence, but it's not picked up. So this was training to general practitioners to help them to identify women, and then obviously they could refer them on and these women would get treatment. So what I really want to show you is the assumptions that we made in the sample size calculations. We assumed that we took account of the variation in cluster size, but we assumed that the analysis was going to use cluster size weights. This was our ICC, this was the mean cluster size, and this was the coefficient of variation we assumed. In the actual, when we got the actual results, we did use a more efficient analysis. The ICC was much smaller than we thought, the mean cluster size was much larger, and the CV was smaller. The real driver in the sample size calculation is this, the ICC. The ICC was much smaller, and it meant that this trial was quite overpowered. The only thing that we might have been able to predict in advance was that we would use more efficient analyses. Okay, we did a careful estimation of these other things, and I don't think that we would have changed anything else. This would have reduced our estimate of the number of clusters needed from 24 to 20, not by very much. And a further trial, I'm not going to go through the details of this, but just to show you the difference between what we thought in the sample size estimation and what we found in the actual trial. Okay, the ICC was smaller again. Again, we did this sample size assuming we were going to use cluster size weights, but in fact we used a more efficient analysis. The mean cluster size was slightly smaller and the coefficient of variation was slightly larger. In fact, when you put all these things together, the trial was slightly underpowered because of the slightly higher coefficient of variation, and we didn't recruit as many individuals per practice as we expected. But it had a power, I think, of something like 78% instead of 80%. Okay. So conclusions, if we carry on doing sample size calculations in this way, I think the sample size estimation is challenging for those conducting these trials. There are simple methods now that exist to account for variable cluster size which should be used, but I think it would be useful to acquire more knowledge, or it is useful to acquire as much knowledge as possible in a particular area to get some idea of what all these different parameters should be within the sample size calculation. The information on patterns in ICCs that we already have is very useful, but we need more information about the coefficients of variation of cluster size. That's if we continue to do them as we are doing them at the moment. There may be other options for the sample size calculations in these trials. Thank you very much.
Yes, thank you for interesting talk and many open problems also interesting. I would like to note that actually this sample cluster size calculations are related directly to modeling patient recruitment and clinical trials.
Sorry, are related directly to?
Related to patient recruitment modeling and clinical trials.
Yes, well,
we developed so-called Poisson gamma recruitment model, and this explains all these things related to cluster size and variation. And by the way, in GSK, GlaxoSmithKline trials, I also saw like medium coefficient of variation like 0.7 based on this. And definitely, as you noted, this in general should be included, this variation, in sample size estimation. We also considered such results Unfortunately, we were not successful to push it really in our practice in clinical trials. But in general, this will, of course, should be accounted if cluster is like effect in a statistical model, right? In this case, of course, it should be included.
Yeah, in the I don't know whether this is a direct answer to the comment or question that you're asking, but in the methodological paper that I showed you some information from, I mean, then we assumed we assumed a Poisson distribution for the patient recruitment, and we assumed something else for the practice recruitment. So there were a lot of assumptions that went into that. The problem with that, as I see it, is that I mean, in that case we had recruitment, dropout, and something else at cluster level and at individual level, and to put all those things in to the model, you know, was not an easy task. And many of us work in an environment where somebody comes along and says, I need a sample size calculation tomorrow, and you can't do that, which was the reason for trying to see if we could use several different methods and say, well, actually, all the methods that you use, you come out with this coefficient of variation in trials in primary care of 0.65. Let's say that's good enough. But yeah, I agree with you. I mean, I would like to do some more of that. But
Yeah, we need to have a change, definitely.
I'm just curious, Sandra, what did you do for analysis for those data sets where the observed ICC turned out to be negative?
we set it to 0.
And just do it in standard method?
Yeah. Well, I don't know whether anybody's got any other suggestions about what we should have done, but that's what we did. Yeah. Fun.
Some people have suggested using the harmonic mean of the cluster sizes rather than the arithmetic mean. And I wonder what the connection between that method was and your use of the coefficient of variation. Is there a direct connection, or is that just an approximation, or what?
I suspect that there's some connection, but I can't answer you off the top of my head. Yeah, it would be interesting to look at.
That has been
I think it has been suggested. Yeah.
I think that's for an unweighted cluster analysis. I think that comes out.
Is it?
Unweighted meaning?
Well, because you talked about your formula was where the analysis was going to be weighted, the cluster was going to be weighted by cluster size.
Yes.
And I think if you don't weight the clusters, I think you end up with a harmonic mean.
Oh, okay.
So the weighting, the sample size method that corresponds to weighting by cluster size, that corresponds to using the harmonic mean? Is that what?
No, I think Ian was saying it's the unweighted. So you're talking about a cluster level analysis without weighting for cluster size. Okay. Well, in that case, just want to thank the other speakers. And let's go for tea.